Good morning, good evening, good afternoon, everybody. Today I'm going to talk about parent-child well relationships across the U.S. unconventional basins, learnings from the data analytics study. This is SPE 209171 from the HFTC conference. This is written by Joe Cosby from EOG Resources and Dr. Mukul Sharma from the University of Texas at Austin. I highly suggest you read this paper because this provides a lot of analysis regarding different basins and different parent-child impact analysis. As usual, please be sure to like this video, subscribe so you can get more content in oil and gas and professional development topics, and please be sure to comment on the video below on the YouTube platform so I can incorporate your feedback into future videos. Thanks so much, and let's get on with the paper. In the study, parent-child well pairs for wells completed within the last 7 years in 9 different unconventional basins are identified using a Python code applied to an Enverus data public dataset acquired in November 2020. These basins include Bakken, Delaware, Eagle Ford, Haynesville, Marcellus, Utica, Midland, Niobrara, Powder River, and Scoop Stack basins. The Python code also performs calculations to create necessary comparative metrics for analysis, and 4 cumulative production proxies are created, which is the first 12 months of BOE, is chosen as the appropriate metric for the analysis. Basin-to-basin comparisons are conducted, and the effects of well spacing and infill timing are investigated. Now I have a couple slides on the methodology. The code organizes well data and identifies parent-child well pairs. The first step of the process was to read the individual well headers data and the well production data for each horizontal well in the basin. The study selected 7 years because there was roughly when horizontal wells started to employ larger completion packages. Subsequently, data cleaning measures ensured that the data was ready for ensuing calculations. Those measures included eliminating a small number of infinite values, converting latitude and longitude coordinates to Cartesian coordinates, and converting date and data to form an adequate for Python. Afterward, total proppant and total fluid metrics were identified in the production data and appended to the well header data for later calculations. With the base data ready to be utilized, the study created 4 production proxies for cumulative production with a range of months of production included for well performance evaluation. The 4 proxies included between the 3 and 14 months of production data. The study ultimately adopted the first 12 months of BOE as production proxy for all subsequent production analysis. All production metrics were normalized by lateral length since a well's lateral length is a key driver for production performance. Since parent-child wells are typically similar in lateral length, the normalizing by lateral length is a typical industry practice. All production analysis is employed normalizing the data. In the cases when the data does not exist, a simple horizontal length was typically used. Gross perforated interval is typically a more accurate measure of the well-stimulated length and less likely to contain errors due to misreporting of well trajectories. Finally, parent-child well pairs are identified within 1,500 feet using a data structure called KD. This method arranges the data by a 2D aerial proximity for efficient filtering to the wells within the desired radius. With the list of pairs available, the well pairs that do not meet and the remaining parent-child inclusion requirements are excluded, and a comparative metrics are calculated for the remaining parent-child well pairs. A maximum 200-foot distance for vertical direction in order to bound the wells and exclude horizontal from entirely different targets. A requirement of at least 3 months of production to avoid a permitted uncompleted or non-produced wells, a requirement that a parent and child operator must use the same operator to minimize flowback differences, and a requirement that both the parent's completion and the first production date must have 3 months in order for a child to avoid co-completed wells, and a requirement that a parent must have 3 or more months of production than the child for the same reason. The code then calculates the metrics in subsequent analysis. Those metrics include a production proxy percent change, a cumulative production percent change, completion time difference, spacing, parent production at the time of child completion, and other metrics. Here's a result of the first 12-month BOE percent change and the well pair distribution by basin since 2017. This is for all of the basins, and this is just to show what the median percent change is between a parent and a child. You'll notice that it is different from basin to basin, or the magnitude is different from basin to basin. Here's the first 12-month BOE percent change box plot and the well pair distribution for the Niobrara at different proppant loading sizes. You'll notice at different proppant loadings there is a different magnitude as well. Here's the first 12-month BOE box plot and their well pair distribution for the Bakken, I believe. And then here's the first 12-month BOE percent change box plot and the well pair distribution by completion date difference by the Delaware Basin. You'll notice that the closer that you are between a primary and an infill well, I call them primary and infill wells, the better that the wells end up performing. So you don't want to delay the timing at which you want the parent well, you want the infill well to be completed. And these are separated by different proppant loadings. Here's the first 12-month BOE percentage change in the well pair distribution for parent-produced BOE at child completion for the Delaware Basin. You'll notice that the better that the parent well produces, the worse the child well ends up being. But that can also be normalized based upon the completion as well. So here are the conclusions of this work. The effect of different variables such as well spacing and child well timing for a given basin are clearly shown in box plots. Different basins display different trends which become obvious for statistical analysis and display of the data. The first 12 months of BOE production is a good way for well performance. It is consistently has 80% of the child well data points within 20% of the cumulative production difference. The scoop stack basins experienced the largest decrease in child well productivity, while the Marcellus Utica wells and the Bakken child wells drilled alongside older parent wells with older completion designs experienced some of the best child well results. Increasing spacing has a clear positive effect on child well production in almost all basins. However, the magnitude of the effect differs from basin to basin. Increasing completion date difference or infill timing typically has a clear negative effect on child well production, but completion design changes can obfuscate this negative impact. Using a parent-produced BOE at child completion is a better measure for depletion than simply timing. Using a parent-produced BOE at child completion corrects for the increase in child productivity observed with larger infill timings. This metric is a better indicator for child performance and parent well depletion. That is the conclusion of this presentation or this paper summary. As usual, please be sure to like this video, subscribe so you can get more content in oil and gas and professional development topics, and please be sure to comment on the video below on the YouTube platform so I can incorporate your feedback into future videos. Thank you so much for taking the time to watch this video, and I'll see you in the next one.